you up on somewhere where we have arrived yesterday. We were looking at tree-level amplitudes in the pure Spinor formalism. I was showing you the opening line to perform these calculations for n massless open string states. The opening line, it starts out similar as in RNS, that you integrate over n-3 punctures after freezing the SL2 redundancy. And then you need the massless vertex operators in two different flavors. There is the position-fixed vertex operator, V, which has conformal weight 0 and ghost number 1. This is our pure Spinor ghost lambda, contracted into some spinorial superfield, having the degrees of freedom of the first external leg. As always, these particle numbers refer to which particles, polarization, and momentum do you find in here. And then there are n-3 instances of the integrated vertex operator U, which has conformal weight 1 and ghost number 0. And at conformal weight 1, there's more stuff that you can write down. That's why you have a total of 4 different worldsheet fields of conformal weight 1. And they are all dotted into some superfield of 10-dimensional super Young-Mills. And BRST invariance of this opening line follows or is equivalent to the field equations of 10-dimensional super Young-Mills, strictly speaking to linear field equations. Okay, and in order to get something more concrete or something where you can compute a low energy expansion, we want to simplify that guy. And in order to do so, we evaluate the CFT correlator in 2 steps. Step number 1 is to get rid of the conformal weight 1 fields that are hiding inside the U's. So here you are basically summing over all possible OPEs. And once you are done with them, then you are left with some zero modes of the lambda and the theta field, the spinors of conformal weight 0. And here the zero mode prescription is written in schematic form, but there's no information loss in hiding the tensor structure because it's unique. Okay, so once you have integrated out the thetas in this way, you get a formal sum of all the Bose-Fermi combinations of amplitudes. You saw it in the 3-point example. You get the 3 gluon vertex plus all the gluon-gluino vertices. So this is how the super amplitudes look like when you go down to components. Okay, you can put anything you like, and I was choosing this in order to have the Young-Mills vertex with a natural normalization at the end of the 3-point calculation. I think it was somewhere here. Yeah, but it's quite brutally engineered. Yeah. It is because you are in 10 dimension, I wonder. Okay, I mean the... Yeah. I think it was, it was entering behind the scenes, the dimensionality. I was showing you some correlators with 3 indices yesterday, where I told you that group theory fixes them. So here you feel that you're in 10 dimensions, or you need to stick in that you're in 10 dimensions. And then by doing all the Kronecker contractions, you find that this gives you a natural normalization for the output. Okay, and I didn't really get through all the derivations of the endpoint function, but I was giving you an idea yesterday how you can proceed if there are some U vertices, if you had 4 points and 5 points. So I was telling you at the end of the lecture that there is an organizing principle for these OPEs, some organizing principle we call multiparticle superfields. I was just showing you the tip of the iceberg, namely the simplest instances of V12 and V123. With more time, I would tell you more things about those, that they essentially obey a recursion, that you can, to a large extent, sidestep the CFT calculations. But let me move straight to the result of using that multiparticle technology. So when the dust has settled and when you discard a sufficient number of BRST exact terms, you arrive at the following result. If you are after the n-point color-ordered open string amplitude, you can expand those in a basis of Young-Mills tree amplitudes. A basis of them where we sum over n-3 factorial permutations of these legs here. And this is reminiscent of which of the external states are represented through the U vertex. Okay, and in order to see that these super Young-Mills tree amplitudes arise, I was giving you some examples yesterday how they look like when expressed in the objects from above. In particular, I was telling you that you need to combine these multiparticle vertices in the right way to get Young-Mills trees, and these field theory amplitudes are in some sense fixed from first principles. You want to be gauge invariant and supersymmetric, which is automatic if you have a BRST invariant combination of these in your pure Spinor superspace description. And furthermore, these guys are engineered to have the right poles, such that you are resonating with the Feynman rules of 10-dimensional super Young-Mills, just paying attention to the 3-point vertices, because quadratic interactions are fixed by gauge invariance. So this is one of the advantages of pure Spinor superspace. You work at the level of superfields where you have good control over the BRST variations. And if everything works at the superspace level, you don't need to worry about the components anymore. You will get the gauge invariance automatically if you were BRST invariant up here. Okay, so these super Young-Mills tree amplitudes arise if you evaluate that correlator in that streamlined manner, and if you furthermore do integral reduction. I meant these integration by parts relations, where you saw some examples yesterday. And I think I didn't get to writing down the endpoint integral, which is showing up as the coefficient of these Young-Mills tree amplitudes. So I will do that now. But before spelling out the details of these disk integrals here, let me stress that this formula separates two different regimes of physics. So on the right-hand side here, we have a field theory object, which in turn captures all the polarizations on the right-hand side, all the dependence on, say, the epsilons and the chi's, if you're really interested in the component answer. So all the polarizations are here, whereas this capital F is independent on polarizations. So here it's a field theory object. But then this is the next sentence. On the other hand, we are discussing a string theory amplitude, so there must be plenty of alpha primes in the formula. And in this organizing scheme, all alpha prime is sitting in the first factor, these capital Fs, that I'll spell out in a minute. So roughly speaking, this disentangles string theory physics in a quantity that solely depends on the momenta, but not on the polarizations. Okay, this is probably clearer when I write down the expression, but yeah, this is just to say this is really pulling apart different regimes of physics which apparently don't talk to each other. I will elaborate on that throughout the lecture under the name of double copy. Okay, so not surprisingly, these capital Fs will be the usual types of disk integrals. Just to remind you, there's the ubiquitous Kober-Nielsen factor In that I will be too lazy to spell out. And then there are some dependencies on the punctures. Okay. And let us note that these are very integration by parts friendly combinations. So here this is already the compactified way of writing them. If you expand out this product, it will start as follows. So this is where you may recognize some features of yesterday's 5-point example. Whoops. It starts like that, and then it has more such factors with a structure of Sij divided by the difference of the punctures. Okay, what else? There is some rho floating around. So this formula is a sum over permutations rho, and for sure, this object F should know about which color ordering on the field theory side we are addressing. And this dependence on the ordering arises right here. The permutation rho acts on all the legs 2, 3, ... n minus 2 that are sitting on the Sij or the Zij. So by definition, it ignores leg number 1, and it acts on the remaining legs which you see inside the Zij and the Sij. Okay, so all this to say the integrand is completely explicit, and I will, in the second half of the lecture, argue that this is in fact a beautiful structure which is reminiscent of the KLT formula for closed strings. Okay, are there any further questions on this endpoint function? Carlo?
Sorry for the maybe confusion. So this 3 amplitude in the string theory side is color ordered.
Oh yeah, right, it is color ordered,
And
yes.
the superamplitude side is also color ordered.
It is also color ordered, yeah, right. You're free to dress this string amplitude with Champeyton factors, and then depending on which alpha prime order you look at, different kinds of color tensors will survive. Okay, you heard it several times. The next steps of the lecture will gear us into the direction of double copy. Yes, please. Ah. Oh, yeah. Aha.
You have different diagrams with a different color ordering, which you would.
Aha.
So it means essentially that given the S channel,
Yeah.
you have many different. You have different color ordering. You cannot represent in the same way what you call S channel here in a different color ordering. You would call ST channel, for example.
Are you worried about the massive poles or the massless ones?
Independently, if you write the order 1, 2, 3, 4, and
Yeah.
the S channel, which
Okay.
is 1, 2.
Yeah, yeah.
You change the ordering, you switch 2 and 3. What do you would now call S channel? It has become the Athena channel. Well, you change the type of diagram.
I mean,
Because,
yeah.
well, okay.
I would maybe it's safest if you just do a relabeling that when you change your color ordering here, then you just relabel everything you see on the right-hand side. But I'm not sure whether I understood the core of the question. No? Okay. Okay. Yeah. I admit this is not very permutation symmetric as it is represented, but I'll give an argument later why it is, or why the correlator's permutation symmetric. Okay, so let me now come to double copy structures in both closed but also in open string trees. Good. I guess I should give you an idea of what I mean by double copy. So let us start with a very naive observation on the string spectrum. Namely, if you study the BRST invariant closed string excitations, you will find that it's essentially enough to know about the open string spectrum. Namely, you need to look at a tensor product involving 2 open string states, and then you exhaust the closed string spectrum. And of course, by level matching, you have to do this separately at each mass level. Namely, the space-time momentum will be the same in the 2 chiral halves of a closed string state, so we should make sure that k square takes the same value in both components of the tensor product. So, you mean an orbifold that mixes left and right movers? Yeah. Okay. So, okay, I did have indeed the 10-dimensional theories in mind, type 2, and also heterotic in 10 space-time dimensions, or bosonic closed string in 26 dimensions. But you're right, there's a caveat to be made that with sufficient orbifolding, you can break up that statement. Yeah. So it is tree level. If I wanted to propagate to loop level, I need to disentangle the zero mode of the x field from the path integral. the del x field. This is something like a loop momentum that you know from Feynman integrals. And if I study the loop integrand in string theory, then this chiral splitting also works for loop amplitudes at the level of the L integrand. If you hear this for the first time, let's discuss it in the break. Okay, so this notion of double copy spectrum applies to each level, but let me zoom onto that statement for the massless case and give you the massless vertex operators of the closed string, type 2. And this is a statement completely agnostic to RNS or pure spinors. Namely, suppose you talk about a closed string state. Then you can effectively factorize it into two open string vertex operators that won't talk to each other inside a correlation function. Okay, so let me go through all these variables one by one. There are spacetime momenta k, which must be the same for left and right movers. And the remaining kinematic variables are gluon polarizations and Gaugino wave functions. And here you can put in different ones on the two open string halves. So these guys over here are possibly different from the unhatted epsilon and the unhatted chi. They are possibly different, but of course also the hatted polarizations must satisfy the physical state conditions of the open string. So even if epsilon hat is different from epsilon, you still want to have transversality, and you also want to have the massless Dirac equation for the fermionic.
Right. It's more restrictive to ask that the K is the same left and right. It is better to ask that they are different. If you think of them compactify one, first of all. And second,
Oh, yeah.
It's better to consider them different because in that way you really see that you have x left and the zero mode of closed string is really made of x left and x right, which are different.
Yeah. So you brought up the buzzword compactify. I fully agree. If you move away from maximal spacetime dimensionality, I may not be in the best approach in this way, but my results are really tuned to having uncompactified spacetime dimensions and no d-branes where the momenta are reflected. Yeah.
Because otherwise the zero mode, if you are completely compactified, the zero mode of the closed string is the same in the left and right. So they talk, they would talk to each other.
Yeah.
This is not the case.
Yeah. So when I write the tree-level amplitude prescription, I will use the disclaimer effective. So I do not want to go into the subtleties of tracking every zero mode individually, but I will give a formula that lands you on the right result, which you, if you are in the maximal and uncompactified space-time dimensionality. But I agree there are a lot of things to take care of when, for instance, d-branes are present. Then I should look at a reflected momentum if I do open and closed string scattering on a disk and do this on D3 branes, D7 branes, and so on. Yeah. So there are a lot of things to which the presentation here is not tailored to. Yes.
So are you saying that every closed string state on shell, you can write it in factorized form, open bar?
Yes.
Shouldn't it be sum of factorized? Because I mean, it's not true, right, that every rank 2 tensor you can write it as a product of two vectors.
Of course, you're free to do linear algebra in the closed string spectrum. For instance, the axion and the dilaton. Well, dilaton is a Neveu-Schwarz scalar, whereas the axion is a Ramond scalar. But you get much better insights on the R-symmetry structure if you combine these two to an axiodilaton. Admittedly, the axiodilaton as a complex combination does not factorize. However, you can always choose a basis of closed string states which do factorize. The axion itself, yeah. Okay, there are also. Yeah, it was.
It's a trick vectorization between this is represented.
Yeah, I think I'm about to write down that formula that you're referring to. So let's look at the double copy structure in the Neville-Schwarz sector. So if you look at the open string boson and double copy it, so to already take the surprise ahead, I will later on give you amplitudes that will be bilinear in each polarization vector. Imagine for state number 1, you have one factor of epsilon and another factor of epsilon hat. This is killing several birds with one stone because you are free to choose your favorite NS and S state. You can either grab the symmetric traceless component, which is the graviton, and so here I'm just doing representation theory. You have a tensor product of two Lorentz vectors, or more precisely little group vectors. And then there is a symmetric traceless Lorentz representation. There's something antisymmetric, the B field. And there's furthermore a trace. To be fully accurate, this is a Kronecker delta inside the little group. I mean, inside the space that preserves transversality. And here is the dilaton. So this comes back to the issue with change of basis. It's only the sum of the three, which is an honest double copy. But you can always do a change of basis. Yeah? So effectively, you're best off to first evaluate the double copy formula and to later on worry about whether you like dilatons or gravitons more. This is the approach that I suggest for closed string amplitudes. And something similar works, of course, if you mix Neville-Schwarz and Raman. Or you can also do a bi-spinner, and then upon fields decomposition, you arrive at the Raman field strengths. Okay, any further question on this idea of double copy spectrum? Yeah. Who's rank 1, sorry?
The particular combination, you are playing that for a particular combination of those three representations get AM probability A hat, right?
Maybe the thing goes the other way around. I will later on write down a square of an open string tree. This square of an open string tree will give you bilinears in polarization vectors. Now, suppose you want to have a graviton amplitude. Then you have to take that square and project the bivector to the symmetric traceless component. And something similar if you want to have a dilaton.
The point is that when you have, if you write a matrix as a product of two vectors, you haven't the same degrees of freedom of all what you have written.
Yes, yes.
The point is that you have to take this bivector and think of substituting with a generic matrix, and then you can split the representation theory.
Yeah.
The degrees of freedom of a bivector are by far less than the degrees of freedom of a matrix.
Oh, sure. But I mean, the left-hand side is multiplicative with respect to the degrees of freedom in epsilon and epsilon hat, right? Yeah, right. 64 states in this tensor product. And this is, right. So in particular here, if you want to, Oh, sure. I mean, you can redo the statement at the superfield level. So if you want to have a supergravity superfield, this would be a bi-spinner if you double copy the unintegrated vertex operator, A alpha dot. No, sorry, not alpha dot, but the second index you can choose whether you're on type 2A or type 2B. And
what you are saying is that you should have an index.
yeah. Okay. Yeah, so maybe the virtues of this approach become more apparent if I spell out the Krt-Level-tie relations, which fix closed string trees in terms of open string trees, at least the traditional way of doing so. So the rough idea of Krt-Level-tie is we have just seen that the spectrum can be represented in a form that closed string on-shell states are a double copy of open string on-shell states. And wouldn't it be nice if this property of the spectrum was also present in amplitude representations? So the idea is to propagate this economic double copy from the spectrum to the amplitudes. And at tree level, this is, let's say, very well understood in the form of the Krt relations that I will spell out. Okay, so no matter whether you do RNS or pure spinor, these two open string vertex operators, the hatted and the unhatted one, they don't talk to each other in the correlation functions. So there is no OPE between V open unhatted and V open hatted. So effectively, the correlators factorize. Of course, this is more subtle when you study the exponentials, the e to the ikx. There you have to work a little bit harder to track the factorization in detail, but let me underline the word effectively. I'm not aiming to go through the intermediate steps with you, but you have my word that you get the correct answer if you work with the following prescription here. So for the type 2 endpoint functions at tree level, what you need to do is evaluate a factorizing correlator or evaluate a product. Oops. So here is one open string correlation function of the type you have seen it before. And here is an independent one over the hatted cousin of the open string vertex operators. I will make a separate comment about the Kober-Nielsen factor, but leaving the Kober-Nielsen factor aside for a second, you will only get holomorphic dependence or meromorphic dependence on the z's in the first chiral half, and only anti-meromorphic z bars in the second chiral half. I'll get to the Kober-Nielsen factor in a second. And of course, you have seen in the RNS and pure spinor section different ghost treatments. So just do the treatments of the ghost in the way you have seen it in the open string sections, separately here and there. It's up to you whether you use the RNS or the pure spinor formalism. Good. What else is there? The integration domain is now adapted to the sphere topology. We are doing closed string scattering. So the worldsheet now looks like this. And importantly, there is no notion of cyclic ordering over the punctures. So I don't need to split into sub-amplitudes. Instead, it's just one object here in the closed string case, where each puncture is allowed to be anywhere on the Riemann sphere. But as before, there's an issue with SL2 redundancy. So this time, at the level of the sphere, it's an SL2C rather than SL2R. I mean, the punctures are not confined to the boundary. So let me give you the closed string analog of the schematic formula from before. I was telling you in the open string case that you should drop 3 integrals. So this time it's complex integrals that you drop. And there's also a Jacobian, which gets now promoted to be the holomorphic square of C-ghost correlator. Okay, and finally, for later convenience, I believe that the most natural normalization has inverse pies. But we can argue about that later. Okay, yeah, I was promising a comment on the Kober-Nielsen factor here. So there were some questions about the absolute value in the open string Kober-Nielsen factor. The way I gave it to you is adapted to address any open string color ordering. So I'm still a fan of having the absolute value in the open string Kober-Nielsen factor. But how can I reconcile this with having that factorization here for the closed string? So the Kober-Nielsen factor for the closed string will be absolute value square, not surprisingly. And given that this is an absolute value square, you can always do a holomorphic factorization. You can present it in a way, Zij to the Sij, and of course the branches of these multi-valued functions have to be chosen in mutual agreement. So also the Kober-Nielsen factor that you produce from this effective prescription has a notion of holomorphic factorization. Okay, so effectively what you do is you put another exponent of 2 next to the Mandelstam variables in the exponent. Okay, so this is the opening line for closed string tree-level amplitudes. And let's note that the integrand amusingly factorizes. Yes, please? Aha, okay. So I think at this point I have no doubt that this is an old story from the 70s. Yeah. The next formula is not quite that old. The next formula will be from the 80s, the Cayley-Parameterization formula. But yeah, I agree. This is something pretty basic. Yes. So the mindset is, let's do the hard work at the level of the open strings. So, for instance, once you have worked hard to chop down the open string correlator, you can insert the results of your work twice into that formula. So this addresses the integrand, but even if the integrand factorizes, this does by no means imply that even the integrals factorize. So this is now the point of the work of Cayley-Parameterization in 1986. So given that the integrands factorize, wouldn't it be nice to also have a factorizing approach to the integrations? And they arrived at the following conclusion: the integrations almost factorize. They are close to factorizing, but there's a small catch, namely they factorize modulo phases. Let me write down a schematic version of that statement. So in the best of all universes, you would decompose all the d square z's from here into a double copy of one-dimensional dz's from the open string. However, this does not quite work. There is some obstruction to do so, the complex phase that I referred to, and schematically speaking, this will be an exponential of the dimensionless Mandelstam invariance. It's these kind of phases that are in your way to do an honest factorization. I will give an example in a minute. And also, what also does not quite factorize, the integration limits here for the open string quantities on the right-hand side. They are also a bit subtle, and this will be some other punctures, some other CJs. You will see examples of that. Okay, so let's go through 3-point and 4-point to see this little caveat in action. So at 3 points, the good news is there is no integration to do, and therefore there is no obstruction of that type if there's no d square z surviving after the SL2. So for the 3-point amplitudes in both type 2a and type 2b, what you need to do is, you do 0 integrations on a product of open string correlation functions. Well, in fact, these correlation functions are independent on the punctures. So therefore, you just multiply the results. Okay, and here the second factor is given a hat, which means that this has the same functional form, how it depends on the polarizations of the bosons and fermions, but you're supposed to replace the polarizations by their hatted versions. Yeah? So the point is that you can choose this epsilon hat independently on the epsilon there. So you have the access to the full triple multiplet. I mean, each state can be independently chosen to be either a graviton or something else, dilaton, etc. So this, if you use the super amplitudes on the open string side, this has all the Raman-Raman or Nebel-Schwarz-Raman sectors in it. Just make sure you pick the right double copy component. Okay, so this is the 3-point Kawaile-Valentine, and maybe this was known well before the Kawaile-Valentine paper, but at 4 points, this is the first time where some real work was to do for KLT. So here, in the 4-point situation, you have one complex integral to do. So roughly speaking, there are 2 real degrees of freedom in your integral. So let's do the usual SA2 frame and leave Z2 as the only integration variable. So as I was saying, there are 2 real degrees of freedom in here that need to be integrated. And a possible choice is to work with the real and imaginary part, x and y. And I won't sketch all the details of the Kawaile-Valentine construction and instead refer you to their paper, but let me summarize the key idea here. Instead of Z2 and Z2 bar, we can talk about the x and y variables here in order to do that integral here. And initially, you start out with real x and y. So this is an honest representation of the Riemann sphere. But now, the idea is, even though x and y are lying on the real axis, let's promote this function of x and y to be holomorphic or analytic in x and y. Let's do the following scandalous move. Let's deform the x and y contour away from the real axis. Okay, let's do the deformation only in the y variables. Initially, y should better be real if you want to exhaust the complex plane. But now, if you think of the integrand as an analytic function in y, you can start doing contour deformations. And ideally, you would like y to become purely imaginary. Why is this desirable? If y is purely imaginary, then Z2 and Z2 bar become real. And we like real integrals because this is what we do in open strings. But there's one catch. You can't quite arrive at a purely imaginary y. You need to be careful that you don't cross any branch points at the integrand. So there is a little real epsilon that obstructs you from doing this best case scenario. Let me show you the meaning of this epsilon in the following plot. So let's look at the Z2 bar variable, and let's look at it after doing that kind of rotation here. So without that epsilon, I would be integrating on the real axis. However, the Kober-Nielsen factor has branch points at the values 0 and 1. So when I do this brutal deformation here, I should not cross the branch points. So it means that in order to stay away from the branch points, you need to do a contour like this. Yeah? You would prefer to be exactly on the real axis, but you can't, since you must not cross these two punctures, these 2 branch points here. Okay, so as you are already hearing it, what we do is some complex analysis here. And in this plot here, I was already going for the worst case scenario. Here, I was already making some assumption on what the value of the holomorphic Z2 is. Let's make the following thought experiment. Suppose I would cross the other branch point above. Suppose we were looking at a contour like this. This would allow us to pull off the contour to infinity. This would allow us to make that integral over z2 bar vanish. So if you are allowed to pick this contour, then you are done. And the only case where you must do the detour below, this only happens if z2 bar is between 0 and 1. That's the only situation where you cannot trivialize the z2 bar integral. Okay, so let's stick to this pessimistic case. Let's stick to those things that contribute. Let's look at that contour. We cannot pull it off to infinity. And the best we can do is we can wrap it around here. Whoops, there's a bit too much green. The best we can do is we can deform that z2 bar contour to run in this way. However, you must make sure that you track the Kober-Nielsen factor in all of these deformations. So from the Kober-Nielsen factor, you get phases to both of these subcontours. Namely, the upper contribution has a positive phase, the lower contribution has a negative phase. And effectively, you get the difference of these two phases, because once you are integrating from left to right, and the other time you integrate from right to left. Let me write down what you get when the dust has settled. Oops. Yes, please. Okay, why there are no... Okay, good point, good point.
We have 3 points, 0, 1, and infinity,
yeah.
And there's 3 branch points. Unless we have very special relation between the matrix and variable, otherwise Z1 and Z3 have different order, and Z6 and infinity is the combination of the sum of the two.
I think the argument goes similar to when you do monodromy relations for open strings. In a good kinematic regime, your integrand vanishes pointwise at infinity. I think it's an argument of this type at work, but let me look it up to double check. Yeah, you mean the dashed one that I wiped out? You're saying?
No, the one that you close, the one that dashed one that you drew before, it's 0, it's fine, because you can contract to 0.
Okay, you agree in the, yeah.
The contour that you are considering now
Yeah.
is not closed.
You mean the one which is wrapping around the branch point here?
You cannot close it infinity.
Okay.
Because there are different sheets.
Yeah. Right. So I won't evaluate it to 0. Or let me see whether you agree with the expression I write down, and then we can probably refine that discussion. So the claim is that following this contour wrapped around the origin, then you should get something like a sine function of S12, which arises as the difference of the two phases. And since we are integrating Z2 bar at values smaller than 0, this gives you a color ordering of that type to take into account that Z2 bar is in that interval between minus infinity and 0. So let me ask back, Carlo, are you comfortable in saying that effectively we are integrating from minus infinity to 0, and we are doing this twice with different phases, where the difference of the positive phase upstairs and the negative phase downstairs gives you a sine function? Does this make sense to you? So you mean open? You mean open in the sense of the Riemann-Mumford compactification, or in which sense?
I mean, ideally, in open string, they would integrate from minus infinity to plus infinity along the real axis, right?
Oh, actually no. I think for the open string, we only integrate in between two punctures for color ordering purposes.
It's an open contour, the segment of it's a line, the cross contour that you do
Oh, yeah. Okay, you are, yeah? Okay. Or can I rephrase what you mean by open contour? Can I rephrase it as saying we are in a definite color ordering? We don't do a sum of all color orderings.
Yes, that's true, but I mean, Carlo was warned
Okay.
about having to draw a closed curve in the complex plane, and with this situation with cuts, you are not in the position of closing the contour, of having a closed curve.
Yeah.
Relating along an open curve.
You are saying that these two subcurves are separated by the branch cut forever. Yeah, yeah, yeah. Okay, I agree. They are separated, and I can't close the contour. Yeah, it is. Yeah. 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 So I agree with you that it is not. It's not that. It's not that. Yeah, we fully agree on that. Yeah. Yeah, yeah.
Why that one is zero?
Okay, so here I was arguing.
Zero, if it's a closed contour, then I can deform to a point.
Right, point at infinity.
Yeah, but if it's a closed contour, if it's still an open contour, then I understand why that one is zero.
No, I'm not arguing that the open contour is zero. On the contrary, the argument was you do get an open contour if the holomorphic Z2 is in the dangerous region being Z2 holomorphic in 0, 1. So this is the situation where you get an open contour. And this is the non-zero contribution to the closed string amplitude. So because I only get contributions in this case, I translate that statement on Z2 into a color ordering on the open string side. So let me stress, these are color-ordered amplitudes in both cases. So this is the selection rule. When do I get contributions at all? And this is my specific choice, how I deal with the open contour in the Z2 anti-holomorphic variable. There are several choices how you can wrap the contour, and this is a valid one, where it's really an open contour as we were discussing. Yeah. So the subtlety of the phases are in this sine function. Okay, so now also at 4 points, we have effectively reduced the closed string amplitude to a product of open string amplitudes. But as you see, there is a bit of decoration that descend from the monodromy phases. And these basic techniques, so again, it's probably rewarding if you go to the Krt paper from '86 and go through the details. And again, you can iterate that trick at endpoints, where the only new thing is a bit of combinatorics. No new ideas. So you will again get a square, or you get some squares of open string amplitudes, and a lot of trigonometry that comes from iterating that trick you have seen at 4 points, or that I've sketched at 4 points. So what the upshot will be, at endpoints, you get more selection rules. There are more open string color orderings where the contours become open. And you can bring these selection rules to a form that, on the holomorphic side, the integration variables should better be between 0 and 1. And here, I'm introducing some element of notation. Whenever I'm not spelling out certain external legs, then I'm hiding them in a Greek letter. So this is a permutation row that acts on all the legs that you don't see, namely these n-3. Okay, so you have already seen here, you are most natural to land on an asymmetric basis under the Cayley trick. So for the hatted open string amplitudes, let me choose a different basis where I'm deliberately swapping n and n-1. Okay, and now I need an endpoint analog of this trigonometric function, and let me absorb all of this into a matrix S alpha. A matrix S alpha whose entries are labeled by permutations rho and tau. So both rho and tau are taken from somewhere in this permutation list, and there are n-3 factorial ways you can do this permutation, and the same for tau. So what this thing is, it's a matrix of size n-3 factorial that I will henceforth call the Krt matrix. And I guess this calls for an example beyond 4 points. So at the 5-point level, this matrix is 2 by 2. There are, of course, different basis choices. So if this formula here doesn't agree with what you have seen in the Cayley-Parameterization paper, then you can check whether there's a choice of a change of basis that takes you there. But in order to have a catchy formula for all multiplicities, I will advocate the following Krt matrix at 5 points. It's a 2 by 2 matrix with 2 sign functions. And the arguments of that sign are always some kinematic variables, some dimensionless Mandelstams. And I just saw I was inaccurate. I should have tracked overall pi's. Okay, so pi squared times the 5-point Krt matrix is this stuff. You see 2 matrix entries spelled out, and the other 2 are obtained by relabeling. And of course, you have to make sure that you go across the diagonals when you relabel. Okay, so at 5 points, it's 2 by 2. You see the matrix entries in front of you. And at n points, you can write down recursion relations for these Krt matrices. So maybe it's better to discuss the details in the break if you are interested in the explicit form. But I think what matters for right now is that this matrix has entries full of trigonometry. So it is a matrix of that size, and the entries have a total of n-3 factors of sine pi, and then some combination of dimensionless Mandelstams. So n-2 factors, let's check it. 1 factor at 4 points, 0 factors at 3 points, 2 factors at 5 points.
What do you mean by alpha prime?
You will later on see its field theory friend when alpha prime gets small. I will need this to distinguish from later. And if you're curious about this subscript 1 here, if you look at the 4 and 5 point examples, the momenta it depends on are K1, K2, all the way to n-2. So this is a reminder of which momenta are in there. And also it's a reminder of which basis choice we have made for the left and right movers. Okay. Two more comments on this n-point Krt formula. I was telling the story for the type 2 superstring, but as long as you don't introduce d-branes, this will be universally applicable to other string theories, namely to all cases where the worldsheet is of the sphere topology. I mean, I wasn't using any details of the A open. I just used some complex analysis properties of the Kober-Nielsen factor, which is the same in heterotic and bosonic strings. So it's universally applicable also to, well, it's just a property of the sphere topology. And it's a trick that carries over to heterotic and closed bosonic tree amplitudes. Whoops. Okay. And a last comment concerns Igor's question about the alpha prime subscript. Namely, the Klt formula holds for any value of alpha prime, but I'm of course free to investigate its field theory limit, its leading order in alpha prime. Let's look at the corollary in the field theory limit. Because then the closed string amplitude will reduce to a supergravity amplitude. Whoops. You get the three amplitudes in type 2a or type 2b supergravity at leading order in alpha prime. And the open string amplitudes will, of course, reduce to the corresponding super Young-Mills trees. And it's quite boring. I'm just copy-pasting the combinatorial part of the KLT formula. But since we are now taking alpha prime to 0, there is a different flavor of this matrix S in the middle. So this will be the field theory incarnation of the KLT matrix. Okay, so let me just give a pragmatic definition. This is the field theory KLT matrix. So its string theory ancestor depends on the kinematic variables through a trigonometric function. And if alpha prime is very small, you can Taylor expand the sign and only keep its leading term. So what you do, you just replace the sign function by its argument. And maybe you see at this place where I like to put the inverse pi's into the normalization, just to make sure that the leading term of the sign doesn't introduce any pi's in the supergravity amplitude. But okay, this is convention. Yeah. So you do this. Ah, yeah, I knew that I was missing something. Yeah, you're right. Yeah. Yeah. Damn it, I was really trying to get the normalizations correct. All right. Yeah, so this is a double copy formula for supergravity tree amplitudes. This is one of the reasons why you may have sometimes heard the slogan that at a perturbative level, gravity behaves like a square of gauge theories. But this is admittedly a form which does not readily generalize to loops. This is, if you wish, a manifestly gauge and diffeomorphism invariant form of making that statement. And there were very interesting developments triggered by Bern, Carrasco, Johansson and collaborators, where they gave further perspectives on KLT, namely a manifestly local description rather than that manifestly gauge invariant one. And one of the virtues of the Bern, Carrasco, Johansson approach was that their manifestly local double copy was much more easily extendable to loop level. So this is how they, among other things, nailed a 5-loop calculation in n=8 supergravity. Yeah, so this concludes what I wanted to say about closed string trees, at least at the level of the integrand. There will be some more info tomorrow on the alpha prime expansion, but if there's no further immediate question on this, I would go back to open strings and argue that the KLT formula also applies to open strings. Yeah, I think as Igor observed, I think I should have put 1 over alpha prime to the n-3 here. Sorry about that. It's probably safer if we discuss it in the break. I don't want to attempt to get it right now. Okay. I was hoping that somebody would get nervous about the bold claim that double copy applies to open string trees. I was deliberately provocating a bit in saying that. Let me now elaborate on why I dare to make this kind of provocation. So the purpose of this section is to go back to these capital Fs that you saw in the open string tree amplitudes, that kind of basis of disk integrals. I mean, this integrand with many Sij over Zij, it was in the first place the result of a calculation. But now I want to try to offer a more intuitive understanding why the calculation was bound to land on these integrands that you saw. And in order to get some rhyme in the integrand of the capital Fs, we need to unfix the SL2 frame. I mean, I was showing you all the endpoint function in a specific SL2 frame, but about the structure of the formula, there's slightly more wisdom if you SL2 unfix. So I will now retell the story of a basis of disk integrals in SL2 covariant way. So I will offer you a set of disk integrals which for sure contain a basis. And in order to have some streamlined notation, let me label the disk integrals by two cyclic permutations. In order to characterize a disk integral, I definitely need to specify the integration domain. I need to specify a cyclic ordering of the punctures. And this can be safely done in an SL2 covariant manner, where I'm not yet committing to which punctures I fix. Yeah, so the first piece of notation is, in the first entry, on the left of the vertical bar, you see the integration domain specified. But this is not the only piece of data to characterize an open string integral. As I was alluding to before, we need to think about the integrand. We need to think about what we integrate. For sure, there's the Kober-Nielsen factor, but there's also the rational function coming from the OPEs. So you saw that there were some denominators, Cij, in the capital Fs before, and let me now give you the SL2 agnostic version thereof. Namely, you can express all the Fs in the open superstring amplitude as a linear combination of these cyclic objects here. And okay, here, this is the boring cyclic ordering, which you already saw there, but a priori, the integrand has no reason to be lined up with a cyclic permutation in the integration domain. So therefore, there are two possibly different cyclic permutations that allow me to label the most general disk integral in the open superstring trees. Yeah, so I hope this double entry notation is all right for you. There are two a priori independent cyclic permutations that characterize the integrals of interest. And I hope that I was more careful with the alpha prime normalization here. Yeah, so this second entry, this row element Sn, characterizes the integrand. Okay, so how does this connect with the open string tree? And how does this connect with KLT relations? Let me address that next. So if we go back, oh, yeah. I agree. I'm badly overcounting here. Strictly speaking, the basis has n-3 factorial elements, so I'm badly overcounting. You're absolutely right. Yeah, so let's go back to the F rows in the open string tree, and let me give you some examples how they can be lined up with these Z integrals. So at 4 points, well, you have seen this object already in the very first lecture. And if you SL2 fix the guy up there, you will find that this is nothing but a Mandelstam times one of these Z integrals. Okay, we were only looking at a color-ordered open string amplitude in the canonical ordering, so it's no surprise that we should put the 1, 2, 3, 4 in the first entry. But now, which of these denominators SL2 fix to the integrand of that? It turns out that you need to do this one with 4 and 3 swapped. It's probably easiest to do the calculation backwards. And let's do one more example. The 5-point version of these Fs, I mean, there were 2 of them, but let me just pick one without loss of generality. This one can be written as some dot products and minus K1 dot K3. It's probably getting boring if we keep on writing examples, but I'm giving you this information to line it up with the Krt matrix. There are some K dot Ks in the same way as they show up in the field theory Krt matrix. This is on the nose, the 4-point S0. And here you can, if you look carefully, you can recognize the entries of the 5-point Krt matrix. Just replace the sign functions here by their arguments. So, motivated by these two examples, let me make the following general statement that at the endpoint level, you will arrive at the following result. You can write the endpoint function as a Klt formula where one of the two sides involves super Young-Mills So maybe you already noticed this. I made a specific basis choice in the presentation of the Klt formula where I held 1 and n-1 and n fixed. The same kind of basis choice you already saw in the open string tree before. Yeah? So this fits quite well. And now, let us take this information into account. I'm now supposed to spell out f row. And from the examples above, you can see, or you can anticipate that the f rows are just the Klt matrix dotted into these z integrals. And if you take a careful look, in all of these examples, we had a twist of the last two legs. So here we are in a basis of 1, tau, n minus 1. Okay, so this is the same kind of twist that appeared before in the Cayley-Parameterization formula for closed strings. And what might not be particularly intuitive, even though we are describing a string theory quantity full of alpha primes, we only get the field theory incarnation of Klt. So here, this is the field theory Klt. So please don't start inserting sign functions. This is without any trigonometry. I mean, you see it in the examples. There's k dot k and not a sign function. Yeah, so how to think about this? Here you see a field theory Klt formula, the same kind of expression that describes supergravity. So if we formally replace this by a Young-Mills amplitude, then this is on the nose supergravity. When trading for a right-moving copy of super Young-Mills trees, then this is supergravity. So morally speaking, the structure of open string tree amplitudes is not that different from supergravity field theory. Yeah. For sure, since S alpha is invertible, you can always do that. Yeah. I haven't. Yeah.
S depends on both rho and tau.
Yeah.
So you cannot really.
Well, I think you can. Yeah.
S depends on rho and tau.
Yeah.
So you cannot really say to replace S with S alpha.
Okay.
Because you cannot pull out something which does not depend on rho.
Yeah.
It depends always on rho and tau.
I'm with you. One needs to be quite careful about these matrix degrees of freedom. So what I had in mind in replying to the question of Carlo, I had in mind that you insert the unit matrix in the space of rows and taus and other permutations, which you can blow up as S alpha times the inverse of S alpha. So the reason why I replied positively to Carlo was that this guy exists. It has been investigated by Sebastian Misera, and intriguingly, this inverse matrix is computing intersection numbers of twisted cycles for you. So this is an object that has found prominent appearance in mathematics, in the framework of intersection theory. So therefore, I'm with you that this is an interesting thing to explore.
You can write it as a superstring, not only the Krt theory.
Yeah, so if you tune this formula to involve S alpha prime, then this gives a explicit solution to the monodromy relations to you. I didn't plan to actively discuss them, but you can reduce those to a basis of n-3 factorial color orderings. It's very easy to write down the equation system, but it's hard to solve it. An A explicit solution to n-point monodromy relations can be found from this trick. So it's good that we were discussing this. Thanks for asking. Yeah, maybe a last comment. In all of this, I didn't use any specific properties of the integration domain. So you can repeat that game for an arbitrary color ordering on the string side. So there's only a minimal tweak in the right-hand side, how the choice of integration domain enters. I mean, the bulk of the right-hand side is just a representation of the correlator. So the correlator doesn't care over which cycle we plan to integrate it. And the only place where reference to integration domains enters is here in the first entry of Z. Yeah.
Is there any field theory that Z can be interpreted as an amplitude for some string theory?
Oh, it's really wonderful that you asked this question. This is the content of the next section. So to amplify what Igor just said, you have firstly seen the Krt formula applying to gravity, where gravity is presented as a double copy of field theories that we knew before, Young-Mills times Young-Mills. So now we see another instance of the Krt formula connecting a field theory with something else. Whatever that something else is, since it appears in a Krt formula, isn't attempting to interpret it as a field theory amplitude in its own right. So isn't it tempting to think of this formula as signaling a double copy, that open strings are Young-Mills field theory times an a priori unknown theory. Let's call it Z theory. So the provocative question is, can we conclude from this double copy formula that open strings are a double copy of super Young-Mills times, let's take the term Z theory as a working title, a theory which is defined by producing these Zs as its amplitudes. So this is, of course, a very bold fantasy. So let me give some evidence that there might be some truth to that interpretation. Let me give some evidence why these disk integrals Z might qualify as an amplitude in a scalar theory. So here I want to connect these disk integrals Z with scalar field theory, scalar and effective field theory. Let me see. I have another 15 minutes? Okay, good. This should be enough to give at least some evidence.
A gauge, higher gauge supergravity in the worldsheet.
Okay.
The supergravity gauge on the worldsheet is n equal to 1. You have just one graviton.
Okay.
If you add the gravitons, you get what I call all n equal to 2 theories, which have only a degrees of freedom,
Okay.
which is called something like Plebanski theory, which is a higher
Plebanski theory. Okay, it doesn't ring a bell at first glance, but maybe maybe you take a look at the scalar theories I present, and then we can see whether Plebanski theory is related to those. Plebanski theory. Okay.
I don't remember.
So let me introduce you to a scalar field theory that might at first glance look pretty unrelated to strings. It's a theory that found frequent appearance in the double copy literature in field theory in the context of the Bernd Carrasco-Johansson duality between color and kinematics. Let's introduce a scalar field with some color degrees of freedom. But now let's go one step further, as in Young-Mills. Instead of a single UN generator, we have our scalar be tensor product valued. Let's take a scalar field which lives in the tensor product of UN and a different UN twiddle. So these are the same old school generators that you've seen a couple of times. But now I'm taking a tensor product of two such generators and accordingly put two adjoint indices on that scalar field. So even though this is not particularly trendy in amplitudes, I will define that field theory by a Lagrangian, namely a kinetic term for the scalar, and also a cubic interaction, which has, as you know it from Young-Mills, some structure constants for the TAs, but also a second copy of structure constants, F twiddle, that encode the commutators of the T twiddles. Okay, so this is really the simplest Lagrangian you can imagine to write down a cubic interaction term for such a bi-adjoint scalar. And you have seen the color decomposition for Young-Mills trees. Given that there's a single copy of T, we can organize the tree amplitudes in traces. But now there are two different species of T's floating around, so you can do this color ordering twice. So this gives rise to a notion of doubly partial amplitudes. It's a bookkeeping trick to remove both color factors from the tree amplitudes in that theory. It contains all alpha primes, yes. The claim is that this Lagrangian computes the field theory limit. It computes the alpha prime to zero limit. I mean, it's in general a tough question to alpha prime expand these things. And this is okay, to get everything, you need an infinite series of effective higher derivative interactions. So I can show you something that Carlos and I did in 2016. We know the equations of motion for the alpha prime corrections, order by order, but not in a resummed form. Yeah, but you're absolutely right. At the moment, I'm just scratching at the tip of the iceberg. So the direction I'm gearing to is to give some zeroth order evidence that Z theory can be thought of as an effective theory of bicolored scalars. Right. Yeah, so the modest step in this direction that I'm about to take, it involves double ordering, where you peel off the traces of the untwiddled T's, and where you furthermore peel off the traces of the twiddled T's. And there's the same bookkeeping game as you saw it in the Z integrals. There are now two cyclic orderings that characterize a given kinematic contribution. So it's the same kind of vertical bar notation which appears over there. In the same way as the Z integrals have two slots, I also need to track two cyclic permutations referring to the color orderings in the trace. So the doubly partial amplitude is that guy over here. It's by definition the coefficient of two different traces, where rho and tau, these permutations can be arbitrarily uncorrelated. Oh, sorry, I wasn't accurate. I was singling out leg number 1, to not overcount. So strictly speaking, it's this, because rho and tau only contain n-1 legs. Yeah, so I was already saying it in words what the next claim about these doubly partial amplitudes is. It is a slick way to compute the field theory limit of the n-point disk integrals. So, of course, the z integrals are series in alpha prime. They carry all the alpha prime dependence in the open superstring. So I'm looking at just a very modest piece of them, the alpha prime to 0 limit. This is where the kinematic poles in a string theory amplitude can be traced back to. And it turns out these alpha prime to 0 limits are on the nose, the doubly partial amplitudes. So there's a lot of string theory literature on the field theory limits, and the paper where this relation has been firstly spelled out in that form is due to Kurt and Yuan here. So this is in the framework of the CHY formalism, which computes quantum field theory amplitudes from punctured Riemann surfaces, but in a way that there's no alpha prime entering. Okay, so you can really take this Lagrangian as a gadget to quickly compute these field theory limits, to bypass the need to alpha prime expand hypergeometric functions.
So in the set over where the O, the definition of the set, you had a rho, which was a computation of the n element. Here you have rho, which is a computation of n minus 1 element.
Yeah.
So over there you should keep consider actually rho.
Oh, well, I don't attempt to be consistent in how many letters my row involves, because in a minute I'll be back to n-3 letters, so my apologies for this kind of inconsistency. Yeah, you're right. It's maybe a different letter would have been more. Yeah. Uh-huh. Yeah. Uh-huh.
And you're taking also the field theory limit for the z, so alpha prime to 0.
Yeah.
Correct.
This is correct.
If I start from my Opensim theory,
Yeah.
and the alpha prime to 0 limit, I get just the Schlotterer amplitude.
Ah, you are asking, yeah. Uh-huh. Oh, you are on the right track. You are asking where does all the noise go if I'm just looking at field theory. Right. The noise cancels. The noise cancels for the following reason. This is the next line. That this, I was already advertising the inverse of the string theory KLT kernel. The inverse of S alpha prime computes intersection numbers. What does this guy compute when I invert it? And this guy computes bi-adjoint scalar amplitudes when you invert it. So the connection to the field theory KLT kernel is that if you go to a specific basis of these bi-adjoint scalar amplitudes, then these are on the nose the entries of the inverse of that matrix. Yeah. And okay, also due to some work by Sebastian Misera, also this is an intersection number, but now it's among co-cycles and not twisted cycles. But you were also asking about the philosophy. So even though this is all about alpha prime to 0, I want to give evidence that the full alpha prime dressed Z functions allow an interpretation as amplitudes, or that this interpretation might be sensical. I'm sorry? Right. Let's go order by order. Let's keep the zeta 2 part of the z's, the zeta 3 part, and for all of them, you can write down terms in a nonlinear field equation for the bi-adjoint scalar. Yeah. So that this is done together with Carlos in September 2016. I can tell you some more details of that. All right, where was I? Yeah, I just concluded the first block of evidence. There is the biojoint scalar hiding inside the disk integrals, namely at alpha prime to 0. But also, let's go slightly beyond alpha prime to 0. Linear. They are not only biojoint scalars, which might be pretty absurd from the physics point of view, but they are also pions, something which is highly relevant for low energy particle physics. So there's a nonlinear sigma model of pions hiding in the low energy regime of the Z integrals. So here I'm looking at a pion field which is valued in just a single copy of UN, not a biojoint field anymore. So a possible representation of the Lagrangian is, or at least the traditional one, it's the Cayley Parameterization, though I admit that in the recent field theory literature there were also some cubic representations of the same action, or of the same field theory. Okay, so here this is the traditional form of presenting the pion Lagrangian, but I believe that different people might prefer different field frame. Okay, and now the next claim is that you can compute the tree amplitudes of this theory from symmetrized disk integrals. What do I mean by symmetrized? Whoops. So we so far looked at a fixed choice of the string theory color ordering. But now I want to do the following. Let's just add up different disk orderings. So if you look at these guys as being embedded in an open string tree amplitude, what you effectively do is that you send all the Chan-Pattern factors to be the unit matrix. So you are scattering photons in open string theory. Or another way of putting it is you're saying that all of your disk punctures are independently integrated from minus infinity to plus infinity. So this is what that object computes. Okay, and now I want to compute its alpha prime to 0 limit and compare it to the pion amplitude. If I do what's written here, I get 0, but I need to know where the first non-vanishing contribution is. Upon symmetrization, this object Z, oh sorry, I was forgetting the most important thing. You sum over the orderings. Sorry. Yeah, so by doing this summation, you kill the field theory limit and many further orders in alpha prime. And the first non-vanishing one is at the order n minus 2. So this factor is just taking you to the first non-vanishing order, such that the alpha prime to 0 limit makes sense and is non-zero. Okay, and the statement here is, if you do this at some color ordering, you compute the color-ordered tree amplitude of these pions up there. And what I found for the normalization is something like I pi to the n minus 2. I hope I was careful on that. Yeah. Okay, so this is the second piece of evidence that there might be some truth to interpreting the disk integrals as some Z-theory amplitudes. I'm sorry, alpha prime? Oh yeah, sorry, I think I set lambda to 1. Or did I send it to alpha prime? Yeah. Yeah, okay. So here, this has an alpha prime expansion that goes like, yeah. And the... Absolutely. So at the 4-point level, it's the zeta 2 part. There are 2 pi's in the zeta 2, and these are the 2 pi's over here. Okay. Yeah. This is not an optimized representation. If I had more time, I would explain how to expose that this is really the low energy limit. But yeah, so this is just the result I wanted to show. That's spelled out in work together with Carlos and JJ Carrasco. Okay, so I guess I should arrive at a point of wrapping up very soon. Yeah, so maybe one last example of effective field theories that are addressable from these constructions. Born-Infeld is, I take the abelian Born-Infeld here, which is by definition the low energy limit of photon amplitudes. So this move of symmetrizing over the disk orderings, this is tailored to compute photon amplitudes, which should contain Born-Infeld. Now, if an arbitrary open string amplitude is a double copy, then so is Born-Infeld. And the first paper to elaborate on this is, again, Cachazo et al. It's this one. And the stringy way of seeing the double copy formula for Born-Infeld, it's really by going through this KLT formula for open string trees. And if you use this result, if you use the fact that there's the nonlinear sigma model hidden in the symmetrized Z's, you arrive at the conclusion that Born-Infeld tree amplitudes obey a KLT formula. Namely, Born-Infeld is proportional to, there are, among other things, n minus 2 alpha primes. Okay, okay, then let me be precise about the alpha primes. I guess this would be sloppy to drop them. The endpoint function has a fixed order in alpha prime. The endpoint function is of homogeneous degree n minus 2 in alpha prime.
Okay, you take it as an effective theory.
Absolutely, yeah, yeah.
Not as a, okay.
Yeah. So at the 6-point function, for instance, there is a f to the 6 vertex contributing, which has 4 powers of alpha prime. And also there's a diagram with 2 insertions of the f to the 4th vertex with 2 plus 2 alpha primes. Okay, so at a fixed multiplicity, so sorry, this is not very readable, at the endpoint level, you can pull out n minus 2 powers on alpha prime, and the rest is alpha prime independent. And this alpha prime independent piece is computed by a KLT formula where super Young-Mills is double copied with the nonlinear sigma model. Yeah, so there are secretly some pions, whoops, sitting inside Born-Infeld. Okay. And to everything I was saying in the last 15 minutes, you can repeat the statements at finite alpha prime. You can do an order-by-order expansion of the disk integrals. Then you can work out alpha prime corrections to the bi-adjoint scalars. You can furthermore track the subleading orders in alpha prime after the symmetrization. And then you get some alpha prime corrections to the pion. So you can, for instance, compare with certain operators from chiral perturbation theory. And finally, you can also work out the subleading orders in Born-Infeld. And for sure, Born-Infeld is quite a heavy truncation of the open string effective action, and there's absolutely no obstacle to go beyond. So all of this is motivation to have control on the alpha prime expansion of these disk integrals. This is what I will discuss tomorrow. Yeah, any further questions on this? Oh, very good that you ask. Yeah. In all these double copy formula, they are additive with respect to the supersymmetries. I mean, the SUSIs from the left movers and from the right movers just add up. So let's take a Born-Infeld. There's for sure no supersymmetry in the pion, but this is meant to be the full super amplitude of 10-dimensional super Young-Mills, or your favorite dimensional reduction thereof. So therefore, this is computing super Born-Infeld, if you wish. I think. Yeah. This gives you the complete tensor structure of all the fermionic amplitudes. I guess this is known under the name Volkov-Akulov. Is that possible? It's nilpotent superfields. Okay. Okay, I guess these amplitudes are more sensitive to the linearized part of the supersymmetry. But if you fix the multiplicity, then you can get the full multiplet structure. Yeah. Okay, okay. Yeah, I think J.J. Carrasco had some thoughts about this, that there might be some spin-off for Dirac-Born-Infeld, Volkov-Akulov Lagrangians. Yeah, so you can really grab the fermion amplitudes here, stick them into the double copy formula, and pick up the corresponding fermion amplitudes for the supersymmetrization of Born-Infeld. Yeah, I mean, this formula applies to the 16-point function, but it does not tell you how to resum different multiplicities. So I guess the open question is how to retell that story at the Lagrangian level. So in the thing you see on the blackboard, I'm forced to fix the multiplicity. Yeah. Okay, thanks.